Welcome back. We solved our technical problems as usually. First of all, let me remind you or tell you again that on the Monday, on the 17th of February, so it's not the Wednesday, it's not the same day in the week, it's Monday on the 17th of February, we'll have our written examination in F005, Blaue Grotte, you know, the other one down there. Okay, I'll remind you again and I'll put it on the internet such that you can see it at any rate. So that's Monday. Okay. Last time I further discussed paradigm theory, which is a descriptive philosophy of science, and especially I discussed the tension that exists between paradigm theory on the one hand and the normative philosophies of science on the other hand, and the tension especially with respect to normal science. I had told you that normal science is a practice, a scientific practice according to paradigm theory, which has a quasi-dogmatic character, meaning that certain presuppositions of science, namely the paradigms and the framework in which you do your normal research, that this framework isn't questioned during the practice of normal science. Now, from the viewpoint of deductivism, this is of course a bad practice of science, because according to deductivism, science should be critical all the time and test everything that it is trying to use. So we have a tension here that the normative philosophies of science say this is a bad practice of science, and paradigm theory simply describes, first of all, this as an existing practice of science, and this tension is something one has to resolve. Now, the answer that is given by paradigm theory is rather simple. It just says, look, what is going on here is just something which deductivism cannot describe at all and cannot evaluate at all, because this is a very weak point of deductivism, namely that you need some sort of principle of acceptance of theories, because otherwise you can't stop testing and test and test and test and never go anywhere. So the fact is, according to paradigm theory, that it's very reasonable that scientists do behave in the way as paradigm theory describes it, namely that in the face of normal science, they are quasi-dogmatic and they don't test their presuppositions all the time, but they apply them. This is reasonable because in this way, scientific knowledge is produced. And on the other hand, once this framework becomes contraproductive, you know, when the framework doesn't help you anymore to solve scientific problems, then scientists will give it up, because then a phase of extraordinary science will begin, and then they will give it up. So you see that the sticking to the framework, as long as it works, is a reasonable practice, and giving it up at the moment when it doesn't work any longer is also a reasonable practice. So what paradigm theory describes is in fact a reasonable practice, and given that, then we can conclude that the normative philosophies of science that evaluate normal science as a bad practice are simply wrong. So according to paradigm theory, one can say normal science is a good scientific practice, and so to speak, that the quasi-dogmatic turns into really dogmatic, you know, a bad dogmatism. That cannot happen, because once you get in trouble in normal science with your guiding framework, meaning that too many significant anomalies appear, then the framework will be given up anyway, because then scientists are so dissatisfied with it, they cannot work with it any longer, that they are then looking for alternatives. So one can say that paradigm theory in this particular respect just provides an answer to these problems that we've seen coming up in deductivism, namely the question, what could be a reasonable principle of acceptance such that we can stop the continuous theory testing. And paradigm theory just provides that sort of answer. So we have now, as far as paradigm theory goes, we have now understood how that principle of acceptance works and why it is a reasonable principle, and why why deductivism's weak point can be, so to speak, healed here with paradigm theory. Okay, are there any questions about what I said in the last session? Anything else turned up in the meantime? No, then we can continue. And first let me make a historical remark about paradigm theory. Paradigm theory was first articulated by Thomas Kuhn in his 1962 bestseller, The Structure of Scientific Revolutions. This book is one of the most successful academic books of all times. It has sold far more than 1 million copies, which is really a large number, has been translated, I think, in 26 languages. It's an extremely successful book, and it, in a sense, dominated is too strong, but was hotly disputed from 62 on, soon after its appearance. And it continues to be discussed in today's literature. So this is Thomas Kuhn. And Thomas Kuhn, perhaps that's interesting. Thomas Kuhn was a physicist by training. He had a PhD in theoretical physics, and then he went into history of science. And then after history of science, he went much stronger into philosophy of science. So he knows what he's talking about when he talks about science, because he has himself practiced science and knows from the history of science much about the former course of science, which is also, of course, necessary if you articulate a theory like paradigm theory. That's what I said. There was a widespread discussion of paradigm theory in many fields, which involved many misunderstandings. So you may read in the literature, perhaps not, but it may happen that you read, for instance, that Kuhn said science is an irrational enterprise and things like that, because people misunderstood what Kuhn meant when he talked about incommensurability. And I told you about incommensurability, that incommensurability says, look, comparing theories across revolutions is a tricky enterprise. It's not that easy. And people had misunderstood that as if Kuhn was saying it's impossible to compare theories across revolutionary divides, which Kuhn never said. He simply said, look, it's very complicated. It's much more complicated than you believe. So there are many, many misunderstandings about this theory around, but you shouldn't care about it. You know now the message, one of the ways how to think about science. Now, also in this theory, of course, I want to address problems that the theory faces, and there are indeed problems that we should discuss now. Now, the first one has to observe is that paradigm theory, as a descriptive theory of science, it describes the course of science, is essentially a statistical theory in the following sense, that the phase model of paradigm theory makes a statistical statement of the form, something like typically or in most cases science develops in such a way, right? It must say that in most cases or all cases, or well, it won't say all cases because there are exceptions, but in most cases science develops in the following way, that we have a pre-normal phase, and then we have the normal phase, and then we have revolutionary science, and then we come back to normal science again. So this is essentially a statistical statement. And the point is then, the problem is, if you look how in other sciences one deals with statistical statements of that sort, then you use really statistical methods applied to the evidence, right? You have certain data, and then you use statistical methods, and then you say, okay, with such a confidence, the hypothesis is right or is wrong given the data, and so on and so forth. So in psychology, for instance, or sociology, or also political science, wherever you have the systematic social sciences, and that would be something like that, because it's about a social activity, namely science, in the history. So if you dealt with these problems, like in the other systematic social sciences, then you would have to validate your statements about normal science and then extraordinary science, revolutionary science, and so on by statistical methods. Well, this has not been done in paradigm theory. Paradigm theory does not use statistical methods. Why not? Well, because it's extremely difficult to do that in history. Historical cases, that's the difference here between the systematic social sciences and history. If you have systematic social sciences and then you say, okay, I want to know, well, I just read yesterday across Europe how happy people are. So different regions are compared with how happy people are, right? And of course, people in Niedersachsen, and especially in Hannover, are the happiest in the world, I guess. People in Greece are fairly unhappy, and they're different. It's a chart where you can see the happiness. This is, of course, a social science enterprise, and the point is, once you know what you want to know, right? Your goal is clear, then what you do is that you collect data in such a way that you can apply the statistics to it, right? You know beforehand what you want to have. You want to have a hypothesis, how is happiness distributed all across different regions in Europe, and then you know, for instance, well, that you need a statistical sample, say, I don't know what it is, say 1 per mil of the population in order to have given a population in each region, say of 100,000 people or something, and then you may know, okay, according to statistics, what I have to do is I have to give questionnaires to 0.5% of these populations, and then I get statistically valid interpretations. Now, the point is that you then collect your data, you know, according to what you need. I mean, that's the same what many of you in your master's thesis do. You know you have a certain hypothesis, and then you think, you consider or ask the question, what sort of data do I need in order to be able to apply statistical analysis to them, right? And that's what you do in natural science as well, and in social science as well. The point is that in these systematic social sciences or in the systematic natural sciences, you can do that. You simply make up your mind and then you generate the data that you need. But you can't do that in history, right? In history, it's just a question, you can't generate data. The data you have to read, you know, you have to read what these people said about their science, and you cannot systematically simply generate the data by experiments as you do in the natural science, right? And in the social science, where you can also generate the data by doing interviews in social research, where you ask people, and then you know you have to ask a certain number of people, and the sort of questions you ask, there's a theory about how such tests are best devised. So you know what you do in order to generate the data, and that's unfortunately not possible in the history of science. So it's very difficult, well, in fact, it is practically impossible to apply these statistical methods on history. That doesn't work. It works in economic history sometimes, because there you have data that are typically already quantitative. But if you look at qualitative disciplines like the history of science, then unfortunately these statistical methods can hardly be applied at all, although one should apply them because the statements are statistical in nature. So this is simply a methodological problem that affects not only paradigm theory, it affects all historical theories that make statistical statements in the end. But that problem unfortunately cannot be solved. But the point is then, in consequence, that you don't really know how good the statements of paradigm theory are, because you don't prove them statistically, which is bad luck, but you can't avoid it. And that means that the validity of paradigm theory's general statements about the development of scientific disciplines is uncertain, right? You may, of course, check a few cases, and that has been done, and you say, okay, yes, in many cases it applies, but you have no idea how many, what the percentage is, for instance, right? And there's a certain uncertainty involved in that, and unfortunately that's unavoidable. Yeah? This is just bad luck. It's just, well, bad luck. It's insofar bad luck as this sort of bad luck always happens when you make statistical statements about history. Not almost, but almost always. So this is a certain problem, and that cannot really be solved. There are, in fact, serious doubts, well-founded doubts, that the phase model applies throughout, that wherever you have a science, that phase model applies. There are certain episodes in science which do not fit this phase model. They are different. That is because, as one knows from other areas of history, history never repeats itself. Every historical case is different from the other one. Never ever, whatever it's political history or art history, if you compare different phases of history or events of the same sort, then if you look a little closer, then every event is different from another one. No political revolution is really the same as another political revolution. No way of generating democracy is just the same as in any other country. All the cases are different. And that is, of course, that belongs the essence of history. This is just our experience. This is just the way history is. And that, of course, applies also to the history of science. So one wouldn't be surprised if you find cases that do not fit the phase model that paradigm theory articulates. And there are, in fact, cases where one can't really say that paradigm theory describes the development of a certain area of science correctly. And one is the development of general relativity from 1915 onwards. I think I said once a little about general relativity theory. It's the theory invented by Einstein between 1905 and 1915. It's the successor theory to Newtonian gravitational theory. It's a theory of gravitation that's very different from Newtonian theory. In Newtonian theory, gravity is a force, right? A real force generated by masses. Masses come with the force of gravity. That's the Newtonian theory. And we have the law of gravitation that says that this force decreases with 1 over r squared, with falling off rather rapidly in a sense. So the theory of the general relativity theory, which doesn't sound like a theory of gravitation, but it is. Okay, and why it is called general relativity, that goes into too many details, was developed and it was successfully tested. I also showed you, or told you, that this Mercury anomaly, that the ellipse of Mercury is turning around, that the 7% of the effect that could not be explained by classical gravity theory, namely Newtonian theory, that this rest of 42 arc seconds per 100 years, that this little rest could be explained by the modified theory of gravitation that general relativity offers. Now the point is that's interesting, that if you look at development of gravitation, of general relativity, which was accepted around after 1915, there was very little normal science after 1919. Normal science that people, have this framework of general relativity, they have their paradigmatic solutions. In 1919, this was the solar eclipse that confirmed a certain prediction about the bending of light due to the sun. This was a big event in 1919, and Einstein became a superstar, an absolute superstar, the Michael Jackson of physics, or Madonna, whatever you prefer. He became a real superstar because he had predicted on the basis of general relativity that light is affected by gravitation. And that is something completely unthinkable in classical physics, that, when you have light and it goes in straight lines, and if you put a big mass here, then the light will be slightly bended around this mass. And that was shown in a solar eclipse, because only then do you have the effect in a solar eclipse that the light from the stars is then passing by very near to the sun. That it does, of course, all the time, but then you can't see the stars when the light comes very near to the sun, because the sun is so bright and then you don't see the star. But during a solar eclipse, you see the stars around the sun. So what you then observed is, in a very famous expedition from 1919 to a solar eclipse, what was observed there, that indeed light is really bent around the sun a little, and that's the effect of general relativity. Oh, you look as if you don't understand. The point is this: we have a star here, and we have the sun here, and we have the Earth here. And the point is that the light of a light that reaches the Earth is by the sun. It's not a straight line anymore, but it's slightly bended. Which means when you look at the star, then and you look in this way, then you look here. Well, you would expect, without the sun, you would expect that the star is here, right here. And when you look with the sun in it, because there's a light bending, then the star appears to be here, right? Because you look in this direction, you look at the light, and you look in this direction, and then the star appears to be here. So the star is, due to the sun, moves outward a little, apparently, if you look at it. And this is an effect that the starlight feels the gravity, right? Light feels gravity, and this is completely unknown in classical physics, and that is one of the effects of general relativity. Now, the point is that in 1919, this prediction of general relativity was indeed observed. When we had this eclipse, only you need an eclipse here because otherwise the sun is too bright, right? But when the sun is then by the eclipse, you don't really see the sun, and you see the stars in the vicinity of the sun, and then you can measure their distance from each other and to other stars, and then you can see this effect. Now, the point is that this was a sort of normal science stuff. You had general relativity. You applied the general relativity to the problem of the starlight, right? And then the prediction was there must be a slight change of the position, very small, by the way. It's 1.5. This here is 1.57 arc seconds. It's a very small effect. You must measure very carefully to see this effect. It's very small indeed. But it was then confirmed, and that was, so to speak, a normal science problem. People expected then, because they believed in general relativity for other reasons, and then they expected that. So this was a sort of normal science problem, but afterwards, there were no problems that could be solved, because there was nothing to which you could apply general relativity theory. There was the perihelion, the motion of Mercury. It was applied to this one. That worked. And after 1919, there was simply no problem to which you could apply the theory, right? Because it's a theory that deviates from the classical of Newtonian theory only very, very little, and only at very special occasions can you see the effects, right? So there were just no problems around. Right? This is different from, say, quantum theory or Bohr's model of the atom. I mean, there were many, many atoms, and you can apply it with a magnetic field and without a magnetic field, and so on and so forth. So there were many problems, and you had really the tradition of normal science. You did not have a tradition of normal science in general relativity. People would have loved it, you know, to solve problems, but there weren't any problems that were solvable, right? There was just no problem you could find. So there was no tradition of normal science. Simply, people had checked the theory. They believed in it, but they couldn't apply it because there were no cases where they really could apply and test general relativity. So there was not really a tradition of normal science there. And then something completely in disagreement with paradigm theory happened, namely that in the 1950s, people started inventing alternatives to general relativity theory, although there were no significant anomalies. And paradigm theory says, look, you stick to your theory that you have in normal science, and you're not questioning it, you're not inventing alternatives, but you apply it, right? That is what you do. But since there was nothing where you could really apply general relativity and look whether the predictions are correct or not, then people started in the 1950s to invent alternatives. Why that? Because they thought, well, if we invent alternatives, we could perhaps make predictions with general relativity and other predictions with the alternatives, and then we can perhaps then measure something interesting which would tell us whether general relativity is right or the alternatives. But this is something which is not the usual case in normal science, because in normal science you don't invent alternatives. I mean, who would invent today in biology alternatives to the theory of evolution, Darwin's theory of evolution? Nobody would, because you apply the theory and you don't invent alternatives. You can't publish alternatives of Darwin's theory of evolution these days, because it's just you have the theory and it works. So why invent alternatives? But in that particular case, the situation was different. It was just impossible to have the tradition of normal science. And this is one of these cases where you see that the pattern, this general phase model of paradigm theory does not apply, and for obvious reasons. So you see again what I said before, every historical case, well, you don't see it really, but this is just a historical case that is really different from the other cases that we discussed so far, namely those cases in which there is a tradition of normal science, and you solve problems, and you give it up once too many problems cannot be solved anymore, and you have too many significant anomalies. So you see this is just an example where paradigm theory does not apply in the literal form, and then of course the question arises, how many such cases exist? You know, cases that do not, where paradigm theory does not apply. Is that a singular case, just one case, a very special case? Or are there more? And that is what I mean. You have a statistical, basically a statistical statements in paradigm theory, and once you have statistical statements, one would like to have the numbers, right, and figures, and say, okay, out of 100 cases, 3 cases or 5 cases or 8 cases or whatever usually are the exceptions to what paradigm theory states. But as I said, it's very difficult or impossible to do that. This is a sort of weakness of paradigm theory, and that's a weakness that is shared by most historical theories that make statistical statements. Okay. Yeah, I think the problem in principle should be clear, I guess, that you see here. And this is what I said already, that in answering this line of criticism, one might simply accept it with the remark that the difficulty mentioned is typical for many general statements about historical processes. This is just life is very bad, very cruel sometimes in science. And that the limited access to historical data prohibits the use of proper statistical tools. This may not be entirely obvious, but the point is that in order to apply statistics, the things that are then subsumed under the statistics must be homogeneous. They must be similar enough such that it is useful to use the statistics. And that is something you usually don't get with the historical cases because they are all different from each other, significantly different, right? And in natural science and social science, we simply force the data to have the homogeneity in order to apply statistics. That's what we do. You know, we devise the experiments in such a way, or we devise the questionnaires in such a way, such that the data generated in this way are can be subjected to statistics. But history, there we have nothing to manipulate. We simply have to take what we get from the sources. So this is just a little unlucky. So the systematic social sciences are in a much better position in this respect because they can often produce the sort of data that are necessary for proper statistical analysis. I think I've said that already. Okay, so this is one of the problems that we have. We have a statistical theory about history, and we have a really certain and unpleasant amount of insecurity of how good the theory is. Right? And unfortunately, this cannot really be avoided. That's just the price to be paid. Now, about the literature, I mentioned this book already from Chalmers, What is the Thing Called Science? And in chapter 8, you find something about paradigm theory. Then I've written a book on that some time ago, Reconstructing Scientific Revolutions, Thomas Kuhn's Philosophy of Science, which is still in press, and you can find it everywhere, I think. And finally, if you really want to, if you start reading, you may either read the little Chalmers chapter here, or you might read Thomas Kuhn's book, The Structure of Scientific Revolutions. Is very, very interesting to read with many historical cases, and you may perhaps enjoy it, which would be the idea of that reading list. And here's another one, rather recent book, Kuhn's The Structure of Scientific Revolutions, a reader's guide. So if you find the book itself too complicated, then John Preston is coming to help. It's a nice little book, very readable and very interesting in some respects. So this is only suggestions. You know that you don't have to do additional reading apart from the lecture here, because you've got many other things to do, and there should be enough material given here. So, are there any questions about that? That is not the case, and then we can go to the next chapter. I must apologize because the next chapter is now on the web, but unfortunately only half an hour ago I could put it on the web. Because I was at a conference. I came back from London last night and I didn't have the time to do it. So we come to the next chapter, if I find it. Yes, here it is. So it is already on the web, and you can download it. It's no problem. And this is the next chapter then on systematicity theory. But first, any further questions now, looking back to paradigm theories? That somewhat clear. So you can download it. You get it as a six-pack, six slides on a page and 3 slides on a page. It's on the internet. You can download it, right? Unfortunately, as I said, I put it on the web only half an hour ago, Okay. Systematicity theory. It's a new chapter now, okay? So, and I start, as usually, with the basic idea of such an enterprise, such a philosophy of science. And the starting point of systematicity theory is somewhat different from the starting points we had so far. And the starting point here is that there are good arguments that the basis of science is not the scientific method, right? The standard story that is told in science and also in social science and natural science, that people say, what is special about scientific knowledge? Well, it is produced by the scientific method, and that makes it special. That's the standard story you probably heard also in your home country, probably in the first year of your education in science, in physics or chemistry or biology or whatever it is, that people said, you know, the speciality or the specific status, the special status of science derives from the fact that scientific knowledge is produced by the scientific method, and that makes it special, right? Now, what would the scientific method be? Well, interestingly enough, if you look in books that talk about the scientific method, and then you ask, well, now tell me, what is the scientific method precisely? Then you get very, very, very different answers. I mean, there's not really a very good answer. There are many answers, but I'm not going into the answers, and you'll see very quickly why I'm saying that. Now, the scientific method would be, if it exists, a set of absolutely binding rules. You know, you must follow the rules necessarily if these rules are supposed to generate the specific character of scientific knowledge, right? They must not be simply rules of thumb. You say, oh, sometimes I follow them, sometimes not. Then the result wouldn't be something special. If the result is something special, then you really must follow the rules. And by the way, one can see that the idea of a scientific method was created basically in the 17th century, and there people explicitly said, you know, you must follow this rule. Yeah? It's no way that you have exceptions. So, for instance, if you have in mathematics, there is a rule. It's not really a method, but it's a rule. Namely, if you make a statement that's not a definition, then you must give a proof, right? This is an absolutely binding rule. You may not say in mathematics, oh, today I'm too lazy to give you a proof for that statement. No, then it's not part of mathematics any longer, right? In mathematics, there's just no way. Either you when you make a statement in mathematics, you must give a proof for it. right? Or it's a definition, then it's fine. If you have a definition, fine, no one cares. But once you make some sort of statement in mathematics, you must give a proof. And there is no exception to this rule. You simply must give a proof. So that is something one has to have in mind, that in science, if science is produced and has a special status by the scientific method, then the scientific method must be something like absolutely binding rules. They would guarantee then the special status. If you say from time to time, oh, I don't follow the rule, I do something else, well, where does the special status come from then? If you sometimes follow it, sometimes not, then I mean, what's then special about science? Okay. So the scientific method would be a set of absolutely binding rules. And now what has happened during the second half of the 20th century, people have looked very closely at historical episodes in order to find the scientific method, or to state that there is no scientific method. They searched for the scientific method. And the result, the somewhat sobering result was this. Whenever you have a candidate for a scientific method, say, in science, in natural science, every good result must be the result of an experiment. Whenever you state something, you must have an experiment, right? That is a candidate for a scientific method, right? You say science is an experimental, natural science is deeply experimental, and whenever you claim something, you must have an experiment that confirms your claim, right? Otherwise, you are not allowed to have that claim. Now, if you have something like that, or you have, say, every hypothesis must be subjected to serious critical testing, right? That may be the scientific method. Whatever you do, the point is this, whatever you propose as a scientific method, you always find episodes in the history of science where people did not follow this. And they did not follow this and got wonderful good results. That's the problem. So whenever you propose a certain something as the scientific method, then I will say, I'll show you an interesting and very good episode in science in which people did not follow what you propose as the scientific method, and by not following, these people were very successful in science. And that then shows that there is no binding scientific method, because whenever you propose something, I'll give you an example where people did not follow it, and it was reasonable that they didn't follow it, right? This was something that was done in the 1970s, 1980s. For any such set, and this is the statement here, for any such set of absolutely binding rules, someone proposes such a set, then there are episodes in the history of science where good scientific results were achieved by not following this set of rules. Right? This is very, very perhaps surprising, but that is what has been done, and the main candidates were discussed in the 1970s, and people said, especially in the case of Galileo, you know, the beginning of so-called modern science in the 17th century, if you propose certain methods how science has to proceed, and you confront that with Galileo, what Galileo did in order to invent the new physics, he did many things that did not conform to these rules, whatever the rules are that you propose. He did very funny things, very strange things. But once you look back and you think, why did he do it? You must say, yes, that was very reasonable what he did, right? In many occasions, experiments and deliberations and whatever he did, he simply didn't follow strict rules. There weren't any strict rules. So the point is then, the result, or the uncomfortable situation, if you wish, is that a scientific method in the sense of absolutely binding rules does not seem to exist, right? Because people got good results in the history of science by not following. This is no suggestion for your behavior in your master's thesis, right? Because usually, in many cases, you do have good methods. The point is more a global one, a global point of view, that you said once you claim all of science is produced by a set of binding rules, then such cases where the rules are not followed and good scientific results were produced, that should not happen, but it does happen. So this is the situation here. And in addition, this is, so to speak, a negative result where you say, look, we don't find in the history of science these absolutely binding rules. That's the negative result. But you also have a positive result from paradigm theory, and I mentioned it at one particular point. I think that paradigm theory is very plausible in describing the mature sciences as working from paradigms and not from rules, right? And the paradigms, as I told you, they are models, and they are indirectly governing scientific research. It's not that they give you explicit rules. They don't say, like in a cookbook, do this and that and that. Sometimes you can translate that in a particular situation in that sort of cookbook rule, but this is not what you derive for every single case in the same way. But you have a paradigmatic solution, and then you take the next problem that looks similar to it, and then you say, okay, I have to solve it in a similar way as I solved the first problem. And that's not a cookbook, right? This is not a rule, a fixed rule. Once you've been said, do it in a similar way. Well, what does it mean? You don't know, right? Do it in a similar way. Yeah, you have to use your brain. And then what would be a similar way if I solve another problem, like, say, in Bohr's atomic theory, like the Bohr atom, like the hydrogen atom? Yeah, do it in a similar way. It's not completely clear what that means. It's not fully determined. So you have to use your brain and reason and ask yourself, how can I do that very productively? So it looks, when you look at paradigm theory, then it looks that the mature sciences work from paradigms. And paradigms are not the same as rules, right? They just say, as I said, it's a rather vague description what you have to do. So one gets the feeling that the general nature of science, if you wish, the general nature of science cannot be described by rules, by the scientific method. And if that is the case, then we cannot characterize the specificity of science knowledge by the scientific method, right? So if we accept this result, this general result here, that such absolutely binding rules do not exist in the history of science, and there were good reasons why scientists in particular cases just did what they thought was reasonable, but not following a particular rule, then the question is, well, what makes then the specific character of scientific knowledge? I mean, we believe that scientific knowledge is better than other forms of knowledge, and the question is, why is it better? What is it? The standard answer is because there's a scientific method. When we see, however, that there is no scientific method, then of course the question remains, so what is it that makes science special? And this is exactly what systematicity theory tries to answer. It doesn't give you, like paradigm theory, a developmental model how science develops, but systematicity theory looks for a characterization of science with some properties, but about these properties I'll talk after the break. So we have something like an 8-minute break now, and then we continue.